Okay, so in this video what we're going to do is we're going to have a look at the unit circle and how it can be used to solve trigonometric equations. We're going to have a look at the theory and then we're going to have a look at some simple examples. The examples can become more complex and we'll probably have a look at those in a later video. But for the moment we just want to get familiar with the unit circle and how we can use it to solve very simple trig equations, the types that might come up maybe at the end of year 11 or the beginning of year 12. Okay, so why do we need the unit circle at all? Because you might be thinking, well, we can just use the graph to solve trigonometric equations, and that is true. There's a few problems that students sometimes have with this. The main one being that they're taught definitions of sine and cosine in terms of right-angled triangles. So we're all used to the SOHCAHTOA, sine is opposite over hypotenuse and all that. And this is fine. The problem is, if our definition is in terms of right-angled triangles, then the largest angle that you can find in a right-angled triangle is 90 degrees. So therefore, expressions such as, say, sine 100 degrees or cosine of minus 10 degrees don't make any sense. You can't have a right-angled triangle with a 100-degree angle in it. And what does even minus 10 degrees mean as an angle? So this doesn't really make any sense. But then students are presented with these graphs of sine and cosine functions straight from this after seeing the definition of sine and cosine from right-angled triangles. And all of a sudden they're expected to work with these objects. And the problem is there's no kind of foundation for them. They're just told that this is the graph of sine and cosine, which in reality is very difficult to link with the sides of a right-angled triangle. And the problem gets worse, I think, because if you put, say, -1, the square root of -1 into your calculator, then most calculators will give you an error. And this is because if you square a real number, then you're going to get something greater than or equal to 0. So if you try and square root a negative number, the calculator is going to throw up an error. And this makes sense, and this is consistent with what pupils are taught. The problem is, if you ask a pupil to type sine of 100 degrees or cosine of minus 10 degrees into their calculator, then it's going to give an answer. It's not going to give an error. Now, this could be a garbage answer, but that would be a very bad design of the calculators, and that's certainly not the case. It's given us some sort of number. Sometimes it even gives us a negative number. How you can arrive at a negative number by dividing the two lengths of the sides of a right-angled triangle, I don't know. But somehow it seems to be evaluating these expressions and giving us numbers which sometimes may be negative. So what is this telling us? What are these numbers that the calculator is giving us? And the problem is it's very difficult to relate it to right-angled triangles. And without any additional explanation, using the graphs can become, like I've said here, a difficult memorization activity. So they're having to memorize the graphs. This is 90 degrees, this is 180 degrees, the sine looks like this, the cosine graph looks like this, the tangent graph, which is even worse, looks like this. And so even before you start to try to solve the trig equation, you've got to recall the right graph, and you've got to recall it correctly, all the key points, the maximums and minimums and roots of the curve, etc. And on top of this, there's 3 different graphs: sine, cosine, and tangent, and and that's if God forbid you try to memorize the ones for secant, cosecant, and cotangent and try and use those. Almost certainly you would revert back to sine, cos, and tan when dealing with equations involving those functions. And so they've got to remember the graphs correctly and choose the right one for the equation. So there's a lot of memorization, and because these graphs really are on shaky foundations, well, they're on no foundations, at least at this level, it can become very tricky. So how does the unit circle help us? Well, it's an alternative way of thinking about sine and cosine visually, other than these graphs. It gives a definition of sine and cosine, for which expressions such as sine of 100 degrees or cosine of minus 10 degrees are perfectly natural. So with the unit circle, sine of 100 degrees is going to be perfectly natural. We'll be able to visualize that instantly. And similarly, cosine of minus 10 degrees, negative angles or negative numbers for the arguments of sine and cosine will make sense, and we'll be able to visualize it very easily. Another benefit is that there's only one picture to memorize, and it's a circle, so hopefully not particularly difficult there. So we've gone from 3 graphs, the graphs having all these seemingly abstract or arbitrary points that we have to remember, to a nice circle. And really the only thing we have to memorize is what 90 degrees looks like, what 180 degrees looks like, but students will already be very familiar with these. In fact, these are the angles from Key Stage 2 and Key Stage 3, rather than what I would say seemingly arbitrary points on the x-axis. Okay, here's 90 degrees, 180 degrees, 360 degrees, it looks like this. On the unit circle, we'll be able to visualize those angles. We can all visualize what 90 degrees looks like. We all know what 180 degrees looks like. We all know what 360 degrees looks like. Okay, so let's get started then. This is the picture of the unit circle, and you might have noticed the subtitle in this video was an ant's tail. And that is because we're going to explain the method of using the unit circle in terms of an ant. So we're going to imagine that we've got an ant who lives on the circumference of a unit circle, and he likes to go for a walk. Sometimes he gets bored of just resting at the point 1, 0. So he likes to go for a walk around the unit circle, but he can only move around the circumference of the circle. So the ant can only move around the circumference of the circle. He always starts at the point 1, 0. If you like, you can think of that as his home. And he likes to go for walks, but he can only move around the circumference of the circle. He can move in any direction. He can move clockwise and anti-clockwise. Initially, we're going to consider him moving anti-clockwise, which we'll associate with a positive angle. So you can see here in this next picture, I've just drawn what we're going to imagine the ant moving to look like. So you can see here that the ant's moved through an angle of θ degrees, and he's moved around the circumference of the circle, and he's at some new point on the circumference of the circle. I've drawn the ant twice just to show his starting and end position, but really there's only one ant. And you can see here that if we draw a line from the ant to the center, then that is the angle that we're going to consider, that with the positive x-axis, which I've called θ here. You can see that the ant, wherever he is on the circle, wherever he is, it doesn't matter, wherever he is, he's going to have an x-coordinate and a y-coordinate. And this is the key thing to remember. Wherever the ant is on the unit circle, his x-coordinate is what we're going to call cosine theta or cos theta. Theta is the angle that he's made with the positive x-axis. His x-coordinate is what we're going to call cos theta. It's not a length, it's a coordinate. Similarly, the ant's y-coordinate is what we're going to call sine theta. So wherever the ant is on the unit circle, his y-coordinate is going to be called sine theta. Instantly we can see that negative value for cosine, all that means is that the ant is on the left-hand side of the circle. A negative value for sine theta, all that means is that the ant's y-coordinate is negative, which means he's on the bottom half of the circle. So instantly we can see that if the ant moves more than 90 degrees, and say less than 180 degrees, his x-coordinate is going to be negative because he's going to be in the second quadrant. And also, cosine of 100 degrees, what does that mean? Well, the ant just moves through 100 degrees. His x-coordinate is whatever his x-coordinate is. So cosine of 100 degrees instantly makes sense, as does sine of 100 degrees. We can see that now instantly. Okay, he's going to move more than 90 degrees. That's going to put him in the second quadrant. And you can see straight away that his sine theta, which is his y-coordinate, is still going to be positive at 100 degrees. But his x-coordinate, which is cosine theta, is going to be negative. So this is the only thing you need to remember. Cosine theta is the ant's x-coordinate, and sine theta is the ant's y-coordinate. They're the only two things that you need to remember. Cosine theta is the ant's x-coordinate, and sine theta is the ant's y-coordinate. That's it. So let's follow the ant on a little journey. Let's suppose that he moves 90 degrees. So again, we're taking movement to be in an anti-clockwise direction, which we'll associate with a positive angle. You've probably already figured out that we're going to associate a clockwise movement with a negative angle, but he's moving in an anti-clockwise direction at the moment. So you can see that if he moves 90 degrees, an angle of 90 degrees, he's up top. What's his x-coordinate there? 0. That means that cosine of 90 degrees is 0. Why? Because cosine is the ant's x-coordinate. What is the ant's y-coordinate up top there? Well, it's a unit circle, so it's 1. So sine of 90 degrees is 1. Why? Because sine is the ant's y-coordinate. He continues on his journey. He now does a 180 degrees, so he's quite far from home. What's his x-coordinate? You can see that his x-coordinate is -1. Therefore, cosine of 180 degrees is -1. Why? Because cosine is the ant's x-coordinate. And you can see here that it's negative. And it makes perfect sense for it to be negative. You can see there's no trickery going on here. His coordinate is negative. Sine of 180 degrees, or sine of 180 degrees is 0. Why? Because sine is the ant's y-coordinate. And you can see that if he moves through an angle of 180 degrees, his y-coordinate is going to be 0. So he carries on. We're now into the realms of quite large angles, certainly larger than you could find in any triangle. So you can see 270 degrees, he moves a 3/4 turn. He stops down at the bottom, has a look at his surroundings. What's his x-coordinate? 0. So cosine of 270 degrees is 0. Why? Because cosine is the ant's x-coordinate. What's his y-coordinate? -1. So therefore sine of 270 degrees is -1. Why? Because sine is the ant's y-coordinate. You're probably getting tired of me saying that, but the reason I keep saying it over and over again is because it's by far the most important thing to take away from this video. So he does a full revolution, 360 degrees. We can see that he's back home. If he does a 360, he's back where he started with. What's his x-coordinate? Well, it's 1. So sine of 360 degrees is 1. Why? Because cosine is the ant's x-coordinate. And sine of 360 degrees is 0. Why? Because sine is the ant's y-coordinate. Okay. We can also immediately see why sine and cosine repeat themselves every 360 degrees. Because it doesn't matter where the ant is on the circle. If he moves through 360 degrees, he just does a full revolution and he's back where he started. So if he's back where he started, obviously his x and y coordinates are going to be the same. And remember, his x and y coordinates are nothing but cosine theta and sine theta. So in other words, cosine theta and sine theta are going to be the same if you add 360 degrees to the angle. Okay, so let's see how we might use this as an example. So we'll start off with something very simple, namely sine theta equals 1/2. And we'll have theta between 0 and 360 degrees. We can solve any trig equation, or any trig equation that comes up at A level, regardless of the range or how difficult the thing inside the argument is. So it might be, say, 2 theta plus pi, something like that. It doesn't matter. We're going to stick with simple examples for the moment, just to get used to using the unit circle. In future videos, we'll consider some more complicated examples. So, sine of theta equals 1/2. Well, if we go to our calculators and take inverse sine of 1/2, the calculator is going to give us 30 degrees. So, sine of 30 degrees is 1/2, and 30 certainly lies between 0 and 360. So what's this telling us? Let's look at a picture. The calculator is telling us that if the ant was to move through an angle of 30 degrees, his y-coordinate, remember sine is y-coordinate, will be 1/2. So I've drawn that on the picture here. The ant has moved through an angle of 30 degrees, and his y-coordinate is 1/2. I've drawn his y-coordinate as a horizontal green line, because obviously that horizontal green line is going to represent a height of 1/2, i.e. his y-coordinate being 1/2. Okay, so that is what our calculator is telling us when it tells us that if you take sine of 30 degrees, you get a half. The ant's y coordinate. So let's pretend that the ant is going to continue on his journey. Now we can see that he would go round, he would go up to the top, and he would start back on the way down in the second quadrant, and bang, he hits that green line again. You can see here he hits that green line again. So at this point, he's also got a y coordinate of a half. Okay, you can see that. So the question now is, and I've drawn the line in yellow here, what is this angle? So we know that the blue line has an angle of 30 degrees, but we can see also that the yellow line, or the yellow angle that I've drawn here, also gives him a y coordinate of a half. It's when he's on the way down. Well, maybe you can use the symmetry of the circle to figure out what that angle is. Can you? Here's a little clue. By symmetry, the angle on the left there must be 30 degrees as well. Well, hopefully now you can figure out what the question mark must be. You know that you've got 180 degrees on a straight line, so that question mark must be 150 degrees. Just before we finish this example, does the ant ever hit that green line again as he moves back to 360 degrees? Well, you can see here that his entire journey would take him round, through the bottom of the circle, back up, and he's not going to hit that green line again. Okay, so we can see clearly that we're only going to have two solutions. He's only going to intercept that green line twice. At 30 degrees, which is the blue line, and then at 150 degrees. So our solution is that theta is equal to 30 degrees or 150 degrees. And they're our solutions between 0 and 360 degrees. Okay, so let's have a look at another example. Let's have a look at a cosine example. Example 2. Cosine theta equals 1 over root 2. And again, we'll have theta being between 0 and 360 degrees. This just represents a complete revolution. We can easily change this range, or in fact go for a general solution using this method of the unit circle. But because this is just an introductory video, we're just going to keep it nice and simple. So if you inverse cosine 1 over root 2, you get 45 degrees. What is that saying? Well, let's look at the picture. That is telling us that if we move through an angle of 45 degrees, or if the ant, rather, moves through an angle of 45 degrees, then his x-coordinate, remember cosine is your x-coordinate, is going to be 1 over root 2. So I've drawn a vertical, this time vertical because I want it to intercept the x-axis, a vertical green line, and that green line will represent 1 over root 2. Okay, so that intercepts the x-axis at 1 over root 2. So we're going to play the same game as before. As the ant moves around the unit circle, is he going to intercept that green line again? Well, let's have a look. He moves round, over to -1, he's far away, comes back round, and you can see that he's almost home, but just before he gets to that final bit, he intercepts that green line again. You can trace it with your finger if you like, start at the point 10, trace it round, bang, he hits the green line at 45 degrees. Go round, bang, he hits the green line again. And the question, just like before, is what is that angle? I put it as a yellow question mark here. What is that new angle? Maybe you can use some symmetry to help you. By symmetry, the angle that I've just put there is 45 degrees. Now can we figure out what the question mark is? Sure. It must be 315 degrees because it's almost a full revolution. We're just 45 degrees short. And 360 minus 45 is 315. Does he hit that green line again? No, he doesn't. He makes it home safely. So our solution to the equation, cosine theta is equal to 1 over root 2, for theta between 0 and 360 degrees, is 45 degrees or 315 degrees. So a natural question at this stage is to ask, what about tan? And what about negative angles? Negative angles are easily dealt with. As I alluded to before, these are going to be movement in a clockwise direction. So positive angles will represent movement in an anti-clockwise direction, and negative angles will represent movement in a clockwise direction. So you can see on the picture here, the ant, as he could get to that point down below by moving, say, 270 degrees, moving through 270 degrees, or he could move minus 90 degrees, because that would represent a 90-degree turn in a clockwise direction. What's his x-coordinate down there? Well, it's 0, so cosine of minus 90 equals 0. What's his y-coordinate down there? It's minus 1. So sine of minus 90 degrees is minus 1. Easily able to visualize that, no problems. What about tan? Well, tan theta is defined to be sine theta over cosine theta. Well, if sine theta is the ant's y-coordinate and cosine theta is the ant's x-coordinate, then tan theta is nothing but the ant's y-coordinate divided by its x-coordinate. Okay, so I've got a picture here. We can see that the ant has moved through some angle theta, and say he gets to the point big X, big Y. Big X is obviously going to be cosine theta because it's his x-coordinate, and big Y is obviously going to be sine theta because that's his y-coordinate. Then tan theta will be big Y over big X, because tan theta is the y-coordinate divided by the x-coordinate. It's sine theta over cos theta. Now suppose that the ant moves through another angle, or an additional 180 degrees. So I've marked that in yellow on the picture here. So the ant moves through an angle of 180 degrees starting from that initial angle theta. So he's going to be opposite to where he was before. His new coordinates are going to be minus big X minus big Y. And you can convince yourself why that would be. Use the fact that that blue line there, that diameter is a straight line, so the gradient must be constant throughout. But what are we going to have if I take my y-coordinate now and divide it by my x-coordinate? Well, by definition, that is now going to be tan of theta plus 180 degrees, which is going to be minus big Y over minus big X. But the minuses are going to cancel, and that's going to give us big Y over big X, which is exactly the same as what it was initially. So it doesn't matter if I add on 180 degrees, tan doesn't change. So just as before, you can add 360 degrees to sine and cosine, and the value stays the same. With tan, you can add 180 degrees. So in fact, this makes tan the easiest one of all, because once we know one solution, to find the other solutions, all we have to do is add or subtract multiples of 180 degrees. In future videos, what we're going to do is we're going to look at how do we solve equations of the type sine of 2 theta equals, maybe sine of 2 theta plus 30 degrees equals. What if the range, the range of values that we're interested in changes? So maybe if it's not 0 to 360, what if it's something like minus 180 to 180? Or what if the question asks for a general solution? In which case we somehow have to categorize all the solutions. Well, the unit circle is going to be very useful there, and in fact it's not going to take us much additional effort at all now that we've got the basic idea behind us. The hard part is done, even though it's not that hard really, visualizing the unit circle. Extending this to more complicated equations is going to be really, really easy if you understand the examples in this video. The graph, not so much. You either have to alter the range or alter the graph. Altering the graph is going to lead to all sorts of difficulties. Thankfully for the unit circle, we're not going to need to change it one bit. It's going to stay exactly the same. Well, I hope you found this video useful. At the very least, it's given you another way of introducing or solving trigonometric equations if you are more familiar with the graphs, which many of you will be. Many of you will no doubt still prefer the graphs, but I hope at least a few of you can see the benefits of using the unit circle, and maybe even a few of you might convert to this method in the future. Okay, thanks for listening, and bye.